You know, deep inside every single microchip, every transistor that's powering our world, there's this tiny, invisible barrier. And for decades, it's been a huge roadblock in physics, a puzzle that seemed, well, almost unsolvable. So today, we're going to dive into how scientists finally cracked its code. It all kind of starts with a simple question. What's the biggest small problem in modern technology? And I mean really small. The answer? It's hidden away at a junction so tiny you measure it in atoms. But it's so important that it affects, and I mean literally, everything with a circuit board. What we're talking about here is the metal semiconductor contact. It's that fundamental connection point in pretty much all of our electronics. Just picture it. It's where the metal wire actually touches the silicon chip. And right there, at that exact spot, there's this invisible gatekeeper. And it's the one that decides if electricity gets to flow and how. Right. And that gatekeeper, it has a name, the Schottky barrier. And for a very, very long time, it's been this kind of invisible wall for scientists. Okay, so this diagram really helps break it down. See, when a metal and a semiconductor touch, the electrons do this little dance. They rearrange themselves. This creates something called a depletion layer, basically an area with no free charges. And what that does is form an energy hill that electrons have to climb over. The height of that hill, that's the symbol phi b right there, that's the whole key. It's like the world's tiniest toll booth, and the toll you have to pay is energy. And believe me, this isn't just some academic curiosity. This tiny barrier directly controls the flow of current. That, in turn, determines how efficient our devices are. I mean, if the barrier is too high or even too low, it can absolutely cripple a transistor's performance. So getting it right, it's essential for, well, everything, from your phone to your car. So you're probably thinking, okay, if this thing is so critical, why can't we just, calculate its properties? Why has it been such a huge mystery for so long? Well, that's the thing. Here was the problem. For years, all the previous attempts were just stuck. You had some models that were what we call empirical. That just means they needed real-world experimental data to even get started. So, not really predictive, right? You couldn't start from scratch. Then you had other theories, the ones based on fundamental physics. And these could only calculate what was happening right at the super tiny atomic interface. They just couldn't see the bigger picture, that full macroscopic barrier stretching out for thousands of atomic layers. That crucial connection between the tiny interface and the larger bulk of the semiconductor, it was just missing. In fact, the scientists behind the breakthrough we're talking about today, they put it pretty bluntly in their paper. They called a complete calculation from first principles a prohibitively difficult task. And that's basically scientists speak for, this is ridiculously, mind-bogglingly hard. But they did it. They actually did it. They developed what's called a first principles theory. And that term is key. It means it doesn't need any experimental data to get started. It builds the entire picture using only the fundamental laws of physics, from the ground up. And their goal? Man, was it ambitious. They wanted to calculate the entire barrier, connecting that weird quantum world right at the interface with the big macroscopic behavior that extends deep, deep into the semiconductor. So, the big question is, how on earth did they do it? And this is where it gets really clever. They use this brilliant process, a self-consistent loop. Think of it like tuning two instruments together. You play a note on one, adjust the other to match, then you check the first one again, back and forth. So first, they take a guess at the charge layout. Then, using good old classical physics, they calculate the shape of the barrier that this charge would create. Then, they bring in the heavy guns, quantum mechanics, specifically a method called density functional theory, or DFT, to recalculate what the charge layout should be based on that barrier shape. And then, they compare. Do they match? If not, no problem. You just repeat the loop, feeding the new answer back to the start. You keep going back and forth until the charge layout and the barrier shape are in perfect harmony. And when they are, boom, you found the real physical solution. And what you get is this beautiful, unified picture. The new method finally connects the quantum weirdness happening right at the surface, these really complex effects that act like tiny energy traps for electrons, with that big, large-scale energy hill that makes up the entire barrier. It bridges the tiny, microscopic world with the big, macroscopic world in one seamless calculation. And that, right there, is something that was simply impossible before. Okay, so a beautiful theory is one thing, but does it actually work? Does it match reality? Oh yeah, it absolutely does. For a classic aluminum silicon contact, a real workhorse in electronics, the theory predicted a Schottky barrier height of 0.59 electron volts. And that number, it's in excellent agreement with the best, most precise experimental measurements we have. So what does that mean? It means we can finally calculate the exact toll for that tiny booth instead of just making an educated guess. The theory worked, period. But it gets even better. The model can do so much more. I mean, look at this. It's predicting the exact layout of charge carriers across the entire barrier for different doping levels. And doping is just the fancy word for the amount of impurities you intentionally add to a semiconductor to tune it. And you can see how the shape of that charge distribution changes and stretches deeper when the doping is lower. The model captures all of these nuances perfectly. Let's put some numbers on that. Here's a really concrete example. With low doping, the model predicts that depletion layer is over 4,000 angstroms wide. But if you crank up the doping concentration, wow, the barrier shrinks dramatically, all the way down to just 67 angstroms. Being able to predict that kind of change, that is an absolute game changer for designing electronic components.
And, this model isn't a one-trick pony. It can predict the barrier's height, its width, and even how all those properties change with something like temperature. It's a complete toolkit for understanding, and here's the important part, for engineering this absolutely critical junction.
So what does this all add up to? It leads to a totally new, incredible capability, engineering the electronics of the future, literally from the atom up. So why does all this matter? Well, it means we can finally move away from a slow, expensive process of trial and error in a physical lab. Instead, we can do rapid, precise design right on a computer. We can simulate brand new materials and new device structures, which just massively accelerates innovation. This is huge for exploring materials that go beyond silicon and for fine-tuning our devices to get maximum efficiency with minimum energy waste. And that really leaves us with one last big thought. For the first time ever, we have a complete, truly predictive theory for one of the most fundamental building blocks in all of electronics. So now that we can actually engineer these tiny toll booths atom by atom inside a computer, the question isn't how do they work anymore? The question is, what are we going to build next?